Good afternoon to everyone. Today's topic is hydrogen and its compounds. Hydrogen and its compounds. In this topic, mainly three parts are there: hydrogen preparations, preparation methods, properties, and uses. First one about hydrogen and hydrides also. Hydrides. It is first part. Hydrogen preparation methods, properties, uses, and hydrides. Second part is water. Here, hard water, removal of hardness of water, methods used to remove hardness of water. And one more, heavy water. Heavy water is nothing but deuterium oxide. Heavy water is deuterium oxide. And the third part is hydrogen peroxide, H2O2. Preparation methods, properties, and uses. It is total topic. Here three subtopics are there. First one is hydrogen preparation methods, properties, uses, and hydrides. Second one is water. In water, what is hard water? How hardness of water is removed by using different methods, and heavy water. Third one is hydrogen peroxide preparation methods, properties, and uses. Okay. Now we are going to discuss about hydrogen. First one. You know already about the isotopes of hydrogen. What are the important isotopes of hydrogen? Important isotopes of hydrogen are protium H11, Deuterium H12. It can also be written like this, deuterium D12. Tritium H13 or T13. These are the three important isotopes. First one is protium. Next one is deuterium. Third one is tritium. Okay. Among these three isotopes, heavier isotope is deuterium. Deuterium is heavier isotope. Radioactive isotope is tritium. Tritium is radioactive isotope. Tritium is radioactive isotope. All these isotopes have same atomic number, different mass number. That means isotopes mainly differ in mass number, number of neutrons, physical properties. Isotopes have similar atomic number, number of protons, number of electrons. Okay. Isotopes of hydrogen mainly differ. Isotopes of hydrogen mainly differ in their mass number, number of neutrons, physical properties. These are the main differences in isotopes of hydrogen. Here, among the three isotopes, protium is called ordinary hydrogen. In ordinary hydrogen, protium content is very high. If you observe the percentages present in ordinary hydrogen contains around 99.98% protium H11, 0.005% deuterium, around 10 power minus 16%, very less, tritium. One of the important point here, by using the three isotopes, possible hydrogen molecules are, by using the three isotopes, possible hydrogen molecules by using three isotopes equal to 6. 6 hydrogen molecules are possible. Okay. How to write these 6 molecules? Here, ordinary hydrogen means H2. Heavy hydrogen means D2, deuterium. T2, radioactive isotope. Hydrogen deuterium, tritium. These are the three isotopes. By using hydrogen and deuterium, we will write one more molecule HD. By using deuterium and tritium, the molecule is DT and HT. 3 and 3, total 6 molecules are possible. Okay. This is about isotopes of hydrogen. Among the three isotopes, protium content is very high, that is proton H11 99.98%. Deuterium content is very less. Tritium is very less. It is radioactive isotope. It is a heavier isotope. It is a heavier isotope. Now we are going to discuss about the preparation methods of hydrogen. Preparation methods. Preparation methods of hydrogen. Here so many methods are there to get hydrogen gas. In so many chemical reactions, hydrogen gas is formed as byproduct also, mainly in organic reactions, in acidic properties of alcohols and phenols. When they react with active metals, we will get hydrogen gas as byproduct. In electrochemistry also, metals with least SRP value than hydrogen. SRP value of hydrogen, you know already, 0. Less than 0 means negative. Alkali metals, alkaline earth metals, they have least SRP values. Produce hydrogen gas. Produce H2 gas from dilute acids. Produce hydrogen gas from dilute acids. Produce hydrogen gas from dilute acids. For example, zinc metal. Zinc has a negative SRP value. When zinc is added to dilute hydrochloric acid, we will get zinc chloride along with H2 gas. Along with the H2 gas. 2 moles HCl is required. Okay. Instead of zinc, if copper is used, no reaction is possible, because for copper SRP value is greater than hydrogen. What is the SRP value of hydrogen? Hydrogen SRP value is 0 volts. Active metals like lithium, sodium, potassium, calcium, they all metals react with dilute acids, produce H2 gas. It is one method. Another one is amphoteric metals like zinc, beryllium, aluminium, tin. They combine with bases, they also produce hydrogen gas. With bases. When zinc metal is added to sodium hydroxide, the product formed is sodium zincate along with hydrogen gas, along with the H2 gas. 2 moles sodium hydroxide, 2 moles sodium hydroxide. One more industrial method is there, Lance process. In this process, steam is passed through iron metal, water vapor. Steam is nothing but water vapor. We will get mixed oxide of iron, Fe3O4, along with hydrogen. 3 moles Fe, 4 moles water. We will get 4 moles hydrogen gas. This process is called Lance process. Conversion of coal or coke into syngas is called coal gasification. This reaction is called coal gasification. Conversion of coal or coke into gas. In this process, steam is added to hot coke. Coke formula is carbon. Steam is nothing but water vapor. Heated in presence of nickel catalyst. We will get carbon monoxide. Carbon monoxide along with hydrogen. This mixture is called syngas. Important. Both are gases. The conversion of coal into syngas is called coal gasification. Here carbon monoxide produced in the above reaction again treated with steam. We will get carbon dioxide gas along with hydrogen. In all these reactions, hydrogen is produced. Name of this reaction is called water gas shift reaction. Here two important reactions are there. First one is coal gasification, another one is water gas shift reaction. Okay. In hydrolysis reaction also, hydrogen gas is obtained at cathode, oxygen gas is obtained at anode. Electrolysis, you know already, electrolysis of brine solution. During electrolysis of brine solution, brine solution is nothing but 10% aqueous sodium chloride. In this reaction also H2 gas liberated at cathode. Hydrogen gas liberated at cathode. Okay, these all are the different methods used to get hydrogen. What about hydrides? The compounds formed by hydrogen are called hydrides. Hydrides are the binary compounds produced by the combination of hydrogen with other elements. Hydrides and their types. Hydrides are mainly three types. First one, ionic or salt-like hydrides. Here examples are important. S block elements mainly form ionic or salt-like hydrides. S block elements. S block elements mainly form ionic hydrides. Among these hydrides, most of these ionic hydrides are ionic in nature except some hydrides like lithium due to small cation. Lithium hydride, beryllium hydride are covalent. They have significant covalent character also. Here lithium small cation, beryllium also small cation. Remaining S block has two groups, alkali metals and alkaline earth metals. They form mainly ionic hydrides. For example, sodium hydride, calcium hydride, barium hydride, like that. One A group element, sodium hydride, 2A group element, calcium hydride. All these hydrides exist as crystalline solids, close pack arrangement, and bad conductors of heat and electricity. Due to absence of free movement of ions, they act as bad conductors and exist in crystalline form. During electrolysis of these hydrides, H2 gas is produced at anode. It is important point. During electrolysis of these hydrides, produce hydrogen gas, H2 gas at anode, H2 gas at anode. Here ionic hydrides are formed by S block elements. They exist as crystalline solids and bad conductors. Okay. Among them, lithium and beryllium hydrides have significant covalent character. Beryllium hydride can also exist in polymeric form. Okay. What about remaining elements covalent hydrides. Next type. Covalent hydrides are nothing but molecular hydrides. Covalent hydrides are nothing but molecular hydrides. These are formed by the non-metals in P block. Formed by the non-metals present in P block. Okay. These covalent hydrides are again classified into three types. First one, electron deficient hydrides. Electron deficient hydrides. Thirteenth group elements. P block contains 13th to 18th. 18th group never form hydrides. 13th group hydrides are called electron deficient hydrides. B2H6 aluminum hydride, AlH3. It exists in polymeric form. They contain less than 8 electrons in valence shell. Valence shell of central atom after bond formation. Here examples are important. Electron deficient hydrides. Next, electron precise hydrides. They satisfy octet rule, but they do not contain lone pairs. Satisfy octet rule, but do not contain lone pair of electrons on central atom. Do not contain lone pair of electrons on central atom. Give example for electron precise hydrides. 14th group elements. Methane, CH4, C2H6, ethane, SiH4, etc. Here examples are important. These are electron precise hydrides. Next, third one, electron rich hydrides. They also obey octet rule. They also satisfy They satisfy octet rule but also contain lone pair of electrons on central atom. Lone pair of electrons on central atom. Okay. Give example for electron rich hydrides. NH3, H2O, central atom oxygen, HF, hydrogen fluoride. Fluorine has 3 lone pairs. Okay. Next, last type, third type hydrides, metallic hydrides. Metallic or interstitial or non-stoichiometric hydrides. Metallic hydrides are formed by D and F block metals. D and F block elements. D and F block elements. In these hydrides, there is no true bond between hydrogen gas and metal. That's why these are also known as non-stoichiometric hydrides. Hydrogen and metal do not combine in definite proportion. All these metals have interstitial space during close pack arrangement. It is the arrangement of metal atoms in a metallic lattice. The vacant space created between the layers of metal atoms is called interstitial space or void. Now this space is filled with hydrogen gas. The resultant hydrides are called metallic or interstitial or non-stoichiometric hydrides. For example, zirconium hydride, lanthanum hydride. In these hydrides, there is no true bond between metal and hydrogen. Based on the vacant space, hydrogen gas is filled. No bond is formed between hydrogen and metal. Only van der Waals forces will exist. That's why this type of hydrides are called non-stoichiometric hydrides. Okay. This is about hydrides, hydrogen. Next part coming to water. What is hard water? Removal methods of hardness of water. Hardness of water is mainly due to when soap is applied to hard water, foam is not produced immediately. The reason is some dissolved salts in water, they cause hardness to water. Hardness of water is mainly due to some dissolved salts. Some dissolved salts in water. They are bicarbonates of calcium and magnesium, bicarbonates of calcium and magnesium, chlorides and sulfates of calcium and magnesium, magnesium chloride, magnesium sulfate, calcium chloride and calcium sulfate. Okay, here bicarbonates causes temporary hardness, chlorides and sulfates causes permanent hardness. Okay, hardness of water is two types, temporary and permanent. Temporary hardness is removed easily by simple techniques, simple methods. During boiling of hard water, the bicarbonates in hard water decomposes and converts into carbonates in the form of precipitate. They are removed by filtration. That's why temporary hardness is removed easily. Simple technique, boiling. Two methods are there to remove temporary hardness, boiling. One more method is Clark's process. In this process also, hard water is boiled. Before boiling hard water, little amount of calcium hydroxide is added. In Clark's process, little amount of calcium hydroxide is added to hot water and boiled. During boiling, the bicarbonates converts into carbonates. In the precipitate form, they are removed by filtration. What about permanent hardness? Permanent hardness are removed by using different methods. Washing soda, first one sodium carbonate, and next one colgan. Colgan is also a complex salt containing sodium. Colgan is a chemical substance. It contains sodium. Zeolite or permutate method. Fourth one, resin method, synthetic resin method. These are the different methods used to remove in above all methods. Hard water is passed through sodium carbonate or colgan or zeolite. Zeolite is also sodium aluminum silicate. Its formula is Na2 Al2 Si2O8 along with water, that is hydrated zeolite. Sodium aluminum orthosilicate. Among these four methods, resin method is modern method. It is modern method. Okay. Degree of hardness of water is how to find degree of hardness of water. Degree of hardness of water. It is generally expressed in terms of parts per million parts. Degree of hardness of water equal to weight of the salt in grams divided by gram molecular weight of the salt. Gram molecular weight of the salt multiplied with molecular weight of calcium carbonate hardness of water is expressed in terms of parts per million, ppm of calcium carbonate, weight of H2O, water sample, multiplied with 100. ppm means, million parts, 10 power 6. 1 ppm equal to 10 power 6 grams. Instead of weight by molecular weight, number of moles of the salt also used. Number of moles number of moles. Ten power 6 is nothing but 1 ppm value. 1 ppm equal to 1 parts per million equal to 10 power 6 grams of calcium carbonate. It is expressed in terms of calcium carbonate. Hardness of water is expressed in terms of ppms of calcium carbonate. Calcium carbonate never cause hardness. Bicarbonate causes hardness. Bicarbonate of calcium, magnesium, chloride and sulfate of calcium and magnesium. Write one problem. One kg of water contains 120 grams of MgSO4. Find degree of hardness of water. Degree of hardness of water. Here the salt that causing hardness is magnesium sulfate. This magnesium sulfate in water causes hardness. Find number of moles of magnesium sulfate. Therefore, degree of hardness is equal to degree of hardness is equal to weight of the salt. Salt weight is given as 120. Divided by what is the molecular weight of magnesium sulfate? MgSO4. Magnesium 24, sulfur 32, 4 oxygen 64. It is also 120. Multiplied with, it is fixed value. Molecular weight of calcium carbonate is fixed value, that is 100 divided by weight of water. 1 kg water is given. 1 kg means 1000 grams multiplied with ppm 10 power 6. Okay. Hmm. 120 cancel. So finally we will get 10 power 5 ppms of CaCO3. If you observe clearly here, degree of hardness of water inversely proportional to molecular weight of the salt. Okay. If different salts are given, among different salts, greater hardness caused by the salt with least molecular weight. If you observe clearly, degree of hardness of water Inversely proportional to gram molecular weight of the salt. Important. Gram molecular weight of the salt. If different salts are given, different salts like MgSO4, calcium chloride, calcium bicarbonate, magnesium chloride. These are the four different salts. Among these four salts, greater hardness is caused by, if you observe the molecular weights for these salts, molecular weights. For MgSO4 120, calcium chloride Cl2 71, calcium 40, 111, calcium bicarbonate, calcium 40, 2 hydrogens, 2 carbons, 24, 6 oxygens, 96, 2 hydrogens, 162. What about magnesium chloride? Magnesium 24, chlorine 71, 95. Okay, these are the molecular weights. Among these salts, which one causes greater hardness to water? Hardness inversely proportional to molecular weight. So, least molecular weight MgCl2 causes greater hardness to water. Now, what about hydrates? Hydrate salts. Give examples for some hydrate salts. The addition product of salt with water is called hydrate. Here, barium chloride along with X moles water, chromium CrCl3 along with Y moles water, copper sulfate along with Z moles water. Identify X, Y, Z, number of moles of water molecules. Salt along with water is called hydrate salt. Here X, Y, Z are 2, 6, 5. Copper sulfate pentahydrate, chromium chloride hexahydrate, barium chloride dihydrate. Some more important points related to hydrogen and its compounds. What about boiling points order? H2O2 hydrogen peroxide has higher boiling point than heavy water D2O, D2O has higher boiling point than H2O. Water boiling point around 100 degrees, it is 101.5, it is around 152. Hydrogen peroxide forms more number of hydrogen bonds. What about melting points order? Melting points order. D2O has higher melting point, H2O2 has lower melting point, 0 less than 0. Heavy water, D2O greater than H2O greater than H2O2. Last one. What about concentration of hydrogen peroxide? Concentration of hydrogen peroxide, concentration of H2O2 solution mainly expressed in 4 scales or in the following scales. First one, percent weight by volume. Percent weight by volume. Second one, molarity M. Third one, normality N. Fourth one, volume strength V. Volume strength V. These all are the different scales used to express concentration of H2O2 solution in different scales. Volume strength is nothing but V. Molarity M. These all are related. For example, if you observe the relation between them for 10 volume H2O2 solution, for 10 volume H2O2 solution, molarity is 0.893. 10V H2O2 solution is numerically equal to 0.893 molar. Normality is doubled, 1.786 normal. Percent weight is around 3.03. Percent weight by volume. Okay, it is the important relation.